Similar to other Mentor PCB tools, there is a Project Explorer on the left-hand side. This contains all of the stackup, layer, electrical nets, and constraint information imported automatically into HyperLynx DRC. HyperLynx DRC will accept most, if not all, available layout formats. The analysis setup contains some system-generated object lists such as power and ground nets, as well as all the physical components of the PCB. It also has user-generated object lists for targeting specific nets in your PCB, such as the DDR or the SerDes nets. Last in the tree is the Rules and Results tab, which contains all the out-of-the-box and custom design rule checks. These are separated by the default categories of EMI, signal integrity, and power integrity. The first rule that we want to run and investigate will be the net near plane edge DRC in the EMI category. This DRC checks for high-speed nets near a plane edge. Switching to the Violation tab, you'll see the violations reported by running the rule. By simply clicking on any of these violations, HyperLynx DRC immediately snaps to and highlights the net that is in violation for this check, making it very easy for the user to identify the issue and then correct it. There is information in the Details window to give advice on how to correct it as well. The next DRC that we will explore is another one from the EMI category called Nets Crossing Gaps. This design rule check will inspect high-speed traces that cross a gap in a split plane without any stitching components nearby. This is a common issue that is tedious to find manually, and HyperLynx DRC will find the violations very quickly and easily for us, saving lots of time for the engineer running the electrical sign-off on his PCB. Note in the Details window on the bottom right, you can see the size of the gap that is in violation. Now let's switch gears a little bit and take a look at an out-of-the-box rule in the power integrity category. The rule that we will inspect and execute is the decoupling capacitor placement DRC. This rule will look at the IC power pins on the PCB and scan within a certain user-specified radius to see if the decoupling capacitors are nearby. Once again, when we have a violation, we'll click on it to analyze it, and we find that IC U505 does not have any nearby decoupling capacitors from its power pin on pin 3. The last category of the out-of-the-box rules is the signal integrity category, and we'll spend some time analyzing DRCs here. The first one we want to look at is the breakout and trace integrity DRC. For this DRC, we will use a portion of its capability to check the neck down on a power trace. After running the rule, we found one violation where the required maximum via our spec was only 100 mils, but we found the trace to exceed that at 143.6 mils. Moving on to some DDR-focused signal integrity checks, let's look at the delay in lane matching DRC. This rule investigates a group of nets delays or lengths and then checks them relative to each other. I will execute this rule on DDR4 address nets, and I'll check for both length and delay while inputting the specs from my datasheet. There is a specified delay and length for DDR4 address nets relative to each other via my Xilinx UltraScale datasheet. Making sure I added every address net to my bus, I will execute the rule. And HyperLynx DRC will make it very easy to identify which of these nets from this address bus are out of length and or out of delay by selecting a violation in the Violations tab. You will see that you get some more information in the bottom right Details window for this DRC. The red net is the violating net, where the green net is the reference net. And you can see the names of those nets in the table. We can see that address net 3 here is the violator in relationship to address net 8 on the DDR4 bus. One thing that's nice about HyperLynx DRC is that if you do not like the units that it reports in, you can go to the Settings tab and change these units to metric. You don't have to reload the database for this change to make an effect. You can simply click on a net in the violation table again, and you can see that it's updated in real time to millimeters now. A similar design rule check to the delay and length matching DRC is the relative delay and length matching design rule check. This rule will also check the length and delay, but it can be customized to focus on two different object lists or two different areas of the board. With the delay and length matching DRC, we use it to check the same grouping of nets, the address nets, versus themselves, the address nets. For this DRC with the relative delay and length matching, we will check the DDR4 address nets versus the clock, which each have their own design-specific length for delays between the two. I'm only choosing to check for delay here so you can see in the violations that NA is reported in the length category. Another DDR3, DDR4 check available from the out-of-the-box rules is the flyby topology check. This rule will check the distance between the IC and the first DRAM in the chain, and then it will check the length between each DRAM, and then the last distance that it will check is the last DRAM to the terminating resistor. In your design datasheet or your specs for your PCB routing guidelines, they will tell you the typical delays to expect between each. HyperLynx DRC makes it very easy to identify automatically where we exceed our route lengths in this topology for the memory routing. Now let's switch gears a little bit and use the signal integrity category rules to focus on some SerDes nets. The differential pair spacing DRC will check the minimum differential pair spacing between two differential pairs. This is a design spec for certain high-speed nets to keep crosstalk levels below a certain amount if routed on the same layer, or even suggesting to route them on different layers. I applied this check to PCIe lane nets, and for this PCB, the PCIe are generation 3. Analyzing the violations for this, HyperLynx DRC highlights the FPGA and the connector that the PCIe nets are routed between, and easily identifies in red the areas where we are not meeting our minimum spacing difference. Binding these portions of nets on the PCB manually would be extremely tedious since they are just segments of the differential pairs. Let's investigate another SerDes signal integrity check, the differential pair phase matching DRC. This rule checks total max skew, total phase max skew, and the max running length of a differential pair. Looking at the rule description, we see a diagram that depicts how the violation is reported and what to look for, where the driving pins are represented in yellow, the phase max skew in red, and the max running length in dark tan. We will again target this DRC on SerDes nets using the PCIe lanes. I will input my driving and receiving component names, and now I am ready to execute my rule and find some violations. In the bottom left corner, you can see how long it takes to actually find the violations, and here it's pretty quick. Now that we have some, let's click on them and inspect. You can see in yellow the driving component pins, and then as it turns to red, this is where we exceeded our phase max skew. Then the color will turn from red to dark tan, and this represents the portion of the differential pair that is exceeding our max running length. There are suggestions in the details box on how to correct this. Now that we have looked at out-of-the-box rules in the EMI, power integrity, and signal integrity categories, we'll switch to show the integration of HyperLynx DRC into Expedition directly. By opening up the same PCB in Expedition, we can start the XAC client, which is the Expedition Analysis Control Client. Here we will see the same out-of-the-box DRCs, but represented in the Expedition GUIs and menus. For this experiment, we will just run one DRC from each category to show that they are reported similarly in the Expedition tool. By selecting an out-of-the-box rule from each category and hitting Analyze Design, we will get progress bars to show how long it takes to run these rules. The next step is to use the Expedition GUI Hazard Explorer to view the violations. This is similar to the Violation tab in HyperLynx DRC. By selecting the breakout and trace integrity violation, we'll see directly on the board in Expedition where that violation occurs. Similarly with the nets near plane edge violations, by clicking them, Expedition automatically switches to signal layer 7 and shows us where that high-speed net is near the plane edge. Since we are already in the layout tool, it makes it extremely easy to apply design changes immediately after running the electrical sign-off.